your host, Kelvin Dewitt, everybody, and we're live.
Okay. Some more terminology. Why did I say I was covering these words? Because I said, oh, I don't think I emphasized them enough, and you're going to see them on your test. So hint, hint. The first one here is what we call the lithosphere. I think I mentioned the word, but I didn't define the word last day. The lithosphere, Kenzie, is the layer of Earth made up of the crust and the uppermost mantle. The lithosphere is where most of the geological action that we see occurs. It's what we can generally see happening in terms of forming mountains and valleys and all that stuff. Below the lithosphere is, I did give you this word last day, it was the asthenosphere. There are other spheres as well, but those are the two that you need to know. The top one is the lithosphere. The one underneath that is the asthenosphere. I haven't come up with a good way to remember which one is which yet. When I do, I'll let you know. One begins with an L, one begins with an A, LA, Los Angeles. I don't know. I haven't come up with anything else. New terminology. Slab pull. Slab pull. And I wrote down here, see the diagram on page 522 for a lovely picture. So if you have page 522 in front of you in your textbook, that would work. The diagram we're talking about is this diagram. Right. Too far, Mr. Dewick. Next one, right here. Slab pull is what occurs when a continental plate or a tectonic plate subducts down into the mantle. I'd like you to imagine that you're standing on the edge of the pool, of a swimming pool, and someone is pushing you from behind, and you're trying to resist them because it's cold, you don't feel like going in, okay? That's what's happening with this ridge push here. This ridge push is pushing this continent from behind, so it's already feeling a force pushing it to the left. It's already feeling, this plate is feeling a force pushing it to the left. Back to your imagination, standing on the pool. Also imagine that there's somebody in the water who's grabbing you by the hand and also tugging. So you're not only being pushed from behind, you're being pulled from the front. You're probably going to get wet. What happens in real life is once this tectonic plate has been pushed a little bit underneath this continent, its own mass is going to start to drag it down into the mantle, just as though somebody was grabbing your hand and pulling you into the water. So it starts to accelerate the process. Not only do you have the ridge push pushing it from behind, but you have the slab pull that once you get enough mass down there, gravity, it's sinking into the mantle, it wants to pull the continent with it. So let's see, I think that's what I wrote in your notes as a definition, I hope. Click, click, click. I said, slab pull. When the edges of a tectonic plate subducts deep into the mantle, it pulls the rest of the plate along with it. Just like if somebody is pushing you from behind in the water and a second person grabs your arm and tries to pull you into the water from the front. So along with convection currents and ridge push, slab pull helps keep the tectonic plates in motion. Those are the three main causes of continental drift, of tectonic plate motion. And I wrote, see the diagram on page 522 for a lovely color picture. A little bit more terminology. So when an oceanic plate collides with a continental plate, the oceanic plate is forced to slide under the continental plate, almost always. Why? It's heavier. Well, wait a minute, Mr. Dewick. Wouldn't a continent be heavier than the ocean because the continent has land? The oceanic plate also has land. It's the ocean floor, but on top of the ocean floor, what's sitting? An entire ocean. That adds a lot of weight. That one will tend to be pushed under. It will tend to sink. So generally, when you have an oceanic plate colliding with a continental plate, the oceanic plate is going to be the one that gets forced under. The continental plate is going to be the one that gets forced above. A deep underwater valley called a trench forms where the plates make contact. And if you turn in your textbook to page 525, you can see a lovely picture of a trench. And I think I have one in your notes from last day as well in color. I think the one from page 525. Yeah, there you go. There's a trench right there. So you have an oceanic plate right here, a continental crust or a continental plate right here. The oceanic plate is being forced underneath, and right around here, some kind of an underwater trench will be formed. Hey, what happens to this stuff here? What happens to this land here? Okay. It's so hot down there, this ends up remelting, re-becoming part of the magma, part of the mantle. And the great circle of life, Simba, the great circle of life, Simba, it all begins to be part of a convection current. And eventually, millions and millions of years from now, this will probably bubble back up to the surface somewhere else. That's what's going on. That's why our world is changing. Back to our notes. The last thing, and I double-checked, it looks like they also like to ask this on the provincial. I didn't think it was important, but since they're asking it on the provincial, they must think that it is important. There are map symbols for the 3 type of plate interactions. Now remember, the 3 types were divergent, convergent, transform. Divergent, Curtis, they slide apart. Convergent, Curtis, they get pushed together. Transform, they slide side by side. There are symbols for each of these. And here's how you can remember them. First of all, when convergent plates get pushed together, what do they form? Mountains. Which one of those 3 symbols looks like a bunch of little mountains? Okay, the middle one. That's the symbol for a convergent plate area. Now, transform, that's when you had a middle boundary and 2 plates sliding in opposite directions. Of the 2 remaining symbols, which one looks like a middle boundary with 2 plates sliding in opposite directions? The third one. Which means the first one is... Now, I don't like that first one because divergent plates are plates that are moving apart from each other. I would have thought, Brady, a perfectly good symbol would have been something like that. I think that would have been crystal clear, but I hopefully have showed you how you can figure it out with a process of elimination. The convergent one makes sense, mountains. The transform one makes sense. The divergent one, well, I'm also kind of saying that in your mind, if you scribble this out, it does look like a lowercase d for divergent. Whatever you come up with, I don't know. Right? I mean, it's a long, stretched out lowercase d, but again, you got to memorize a bunch of junk for the provincial. I hate memorizing stuff, but the provincial wants you to memorize stuff, so I'll try and give you different ways that you can pick these up. So, I've pasted this picture down below, but if you want the color picture, you'll find it way easier to turn to page 523 in your textbook. You'll see this picture here, but I don't think it's very clear in your notes, is it? So if you got your textbook, turn to page 523. If you don't, you'll have to use the diagram in front of you. Here is a map of the planet, flattened out, complete with the various symbols. Now, they gave you the legend, the key here. So arrows are what direction the plates are moving. A horizontal line, a single line, is where there's a transform boundary. There's where there's a transform fault, a divergent boundary, and a convergent boundary. So I want you to see if you can take a few minutes. I'm going to put 5 minutes on the clock. See if you can answer 1, 2, 3, 4, 5, 6, and 7. There's going to be more than one answer to these, and we're going to discuss the answer. So try and find 2 plates that share a convergent boundary. Try and find 2 more plates that share a convergent boundary. Find 2 plates that share a divergent boundary. This one is tougher to find. Find two different transform faults. What two plates? Find two plates moving away from each other, two plates moving towards each other, and two plates moving alongside each other. Try this on your own or with a neighbor. Earthquakes. This is 3 days old. I did this on Saturday. I went to a website and I said, hey, what are the earthquakes in BC for the past 30 days? That's accurate. We are in a fairly high earthquake zone. Thankfully, no huge ones that are 6+ on the Richter scale. Mostly small, minor tremors, but we have had some very massive earthquakes. And they had an earthquake alert, so April 13th, today is the 17th, 2:39 a.m., a magnitude 4 earthquake occurred off the west coast of Haida Gwaii. There was a massive one off the west coast of Haida Gwaii last year, big enough that there's a set of ancient hot springs that's a tourist attraction that people have been going to for, we think, 2,000 or 3,000 years, because the First Nations people have used it for centuries. It dried up completely. The water, they went back there, it's gone. So there is some serious underground tension going on out there. Tune in next week for see what happens, or a couple of years from now. We're due for a big earthquake. A couple of pictures. Earthquake examples. So, yeah. We are near the Juan de Fuca plate transform convergent boundary fault. There is certainly every reason it could occur low enough in the earth that we'd still, at an angle, we'd still feel it. But yeah, it could certainly happen here. Probably north of us, probably closer to Vancouver Island, but earthquake prediction right now is still very, very tough because these tectonic plates move so slowly. They're very difficult to detect, and it all happens underground. A couple of significant ones. So in 1946, on Vancouver Island, there was a magnitude 7.2. There's some black and white photos. And Seattle, Washington in 2001, you may recall that. Were you guys alive? You were young, but you may recall that one. Our school shook. We felt it here. I was sitting in my room doing marking, and a teacher came in and looked at me. It's an earthquake. We were quite psyched as science nerds, and then we went, oh, I guess we better actually do the drill. It happened between classes, so doing the earthquake drill didn't quite work because the students were in the hallways, but we had to, evacuate the school and all that stuff. That one considerably larger. It's amazing. So, earthquakes, some terminology. The focus is the location where the earthquake starts somewhere down below in the earth. So an earthquake, Jake, starts somewhere down there. If you draw a straight line right up to the surface above the focus on the surface of the earth, we call that the epicenter. The epicenter. So you'll hear them use that word in the news. They'll say, where is the epicenter? That is on the surface right above where the earthquake occurred. Earthquakes can be shallow or deep. Shallow, closer to the surface, causes more damage. There's probably thousands of earthquakes very, very deep going on all the time. But as long as they're way down there, their energy doesn't reach us. How do we measure the magnitude of earthquakes? What scale do we use? You guys have heard this term before? No. The Richter scale, named after a scientist whose last name was Richter. But people don't have a good understanding of the Richter scale. The Richter scale, Hayden, is kind of weird. First of all, it measures the intensity using what's called a seismometer, a seismograph that measures the vibrations in the earth. The Richter scale is a scale that goes up by powers of 10. In other words, the difference between a magnitude 6 and a magnitude 5 earthquake, it's not that it's 1 times stronger, it's 10 times stronger. You know what? We have an abbreviation in math for times, don't we? 10 times stronger. And that's why you may think, well, those numbers sound really similar, but why was there so much more damage over there? Hey, that was a 7.8, this was a 5.2, 7.8 and 5.2. Those numbers are fairly close together. No, that's a huge amount of difference in damage. Magnitude 5 compared to a magnitude 3. What's 5 take away 3? It's going to be 10 squared, or a 1 with 2 zeros, times stronger. 100 times stronger. So when you get to a magnitude 7, which does significant damage, a magnitude 2, you can feel. A magnitude 2 is what you feel if you're parked in your car waiting for the train and the train is going by and you can feel the rumbling through your car from the train. That's about a magnitude 2. You can feel it. A magnitude 7 is not 5 times stronger, because that's what a lot of people think. They'll go 7 take away 2 is 5. It's 10 to the 5th. It's a 1 with 5 zeros. 100,000 times stronger. Roughly, it'll do 100,000 times more damage. So magnitude 2 can be felt. Anything above magnitude 6 does some damage. Darian, partly answering your question, here's our home. We have the Juan de Fuca plate. We have the North American plate. We have the plates moving away from each other in this area. And we have partial melting. We have a subduction zone. You know what? There was a big earthquake, we think, in about 1700. We can detect that from the cracks in the rock. And we've had a few others going on. And, well, very high right there. High right there, 1965. There was a big one in 1872. You can see, Darian, most of them seem to be occurring out in the ocean, but not all of them. Answer your question okay? Yeah. Earthquakes make the ground shake, and we categorize this ground shaking into 3 types of waves, seismic waves. The first type is called the primary waves. The primary waves. We abbreviate them, we call them P waves. P for primary. These travel through the crust, but they'll travel through solids and liquids and gases. The ground compresses and stretches in the direction of travel, and they are the first to arrive. They travel at around 6 kilometers per second. As soon as we detect those, because primary waves don't do that much damage, they do some, we have a very short window to start warning people. If we detect the primary waves, the next one's, well, it begins with the letter S. What comes after primary school? Secondary. The secondary waves. The S waves. Kenzie, these ones also travel through the crust, but they don't travel through liquids that well. The ground compresses and stretches perpendicular to the direction of the travel. I'll show you an animation in just a second. They're the second one to arrive. They travel at about 3.5 meters per second, so almost half the speed, a little more than half the speed. They're also called shear waves. They do more damage than P waves. The third type of wave are called love waves. We call them L waves. They are the last to arrive. What would an easy way be to remember that the L waves are the last to arrive? I got nothing. Scientist whose last name was Love, yep. Why does it say what? Why does it say surface? Yeah, I haven't got there yet. Patience. Okay? So, in answer to your question, Miller, here's a better description of the 3 types of waves. So the primary ones, they're a type of body wave. They arrive the fastest. That's the ground doing this back and forth. That's the ground shaking back and forth under your feet or under a building. It does damage, but buildings can handle a fair bit of sway. We have to build them already to take some sway just due to wind blowing on them. So it's not too bad. They travel through solids, liquids, and gases. They're fast. The secondary waves, these are the ones that do a lot of damage. That's the ground moving up and down. That's the ground moving up and down. That's what does a lot of damage. Buildings aren't really designed to go up and down like crazy. The third type, L waves, we call them surface waves. They don't travel through the mantle. They don't travel through the lower crust. They just travel along the very, very surface. And they're a more recent designation because we separated secondary waves. We said, you know what? There are actually two types. There's a secondary wave that's also traveling under the ground, moving things up and down. And then there is a surface wave, an L wave, a last to arrive. The ground motion is a rolling action like ripples on a pond. If I wanted to give you an illustration, it would look something like this. Okay. We have earthquakes where there are plate boundaries. Also where there are plate boundaries, we have volcanoes. Volcanoes. We have three main types of volcanoes. We have what we call composite volcanoes, shield volcanoes, and rift, R-I-F-T, volcanoes. They all behave slightly differently, and they all have different magnitudes, different violences of eruptions. Some erupt very violently, some just trickle away quite conveniently. Composite volcanoes. When I say volcano, this is the one most of you think of. This is your standard volcano. It's cone-shaped. Well, Mount Baker is a composite volcano, and you've all seen Mount Baker. Composite volcanoes have very thick magma. By the way, what's the difference between magma and lava? I think lava is when it's above the surface, and magma is when it's below the surface. I won't be that fussy, and I'll have to double check that, but for what it's worth, if you're wondering. And these occur at plate boundaries. Pictures. So here is a composite volcano. These ones tend to erupt quite violently because the way they're set up, it is entirely possible for this passageway to get blocked by rock if it hardens, and for the pressure to build and build and build and build and build, so that you go from lovely, lovely to that. Oh, and you can see another small composite volcano is beginning inside. In fact, this is a cool picture right here. You can see the kids are holding the before and the after. That's what it looked like. I think this is Mount St. Helens. Before, that's what it looked like after. Okay. So what happens then is you have some kind of a magma chamber. You have a plate boundary so that there is a weak area in the crust, enough for the hot magma to flow up to the top. When it hits the solid air, it tends to cool off, and it flows down the mountain, and it forms a small cone. Then it erupts again, and you get another layer of rock. It erupts again, you get another layer of rock. In fact, if you dig through volcanoes, you can pretty accurately tell how many times they've erupted, because you'll notice the rock changes its pattern every time it hardens, unless it was erupting continuously, but usually the composite ones don't do that. Eventually, you get Mount Baker, volcanic ash. Can you make a volcano? Sadly, I don't think we'll be doing that in this, but I think you guys do it sometimes in earth science, but don't quote me on that. You're assuming, by the way, I assume, Emily, you mean a fake volcano, not a real one? Fire bad? Well, you know. Second type is a shield volcano. So turn the page. Shield volcanoes tend to be very large, but flatter than composite. In fact, they look an awful lot like a round warrior's shield laid flat on the ground. That's why they're called shield volcanoes. If you see the old roundish Viking shields, they look an awful lot like that. Thinner magma, so the eruptions are much less violent. They form over hot spots, which are weak spots in the lithosphere. So here is a lovely cross-section of a shield volcano. Often they will have lava flows still underneath the rock along the sides of the mountain as well, because they don't have that huge explosion. They don't erupt so violently. The lava can trickle and trickle and trickle, and if the top part of the lava turns solid, that might be enough insulation for a lava tunnel to form, and lava can continue to flow underneath. Pictures? I will in a second. So here's an example of a shield volcano. You can see it's much, much flatter. And the lava tends to run down the mountain, not explode and go shooting into the air. Matter of fact, the Hawaii volcanoes are shield volcanoes. So Kilauea volcano has been erupting since 1983. These lava flows have added over 568 acres of new land, covered 8.7 miles, 14 kilometers of highway, with lava as deep as 115 feet. So it slowly flowed over the highway. They wouldn't have built the highway there 40 years ago if they had known that it was going to erupt. But it's a nice, I'll call it a safe, controlled eruption, Emily. You got to move stuff out of the way, but generally no one's dying. Okay?
Can I ask a question?
Sure. Emily, there you go. Oh, sorry, Kenzie, there you go.
Park. Oh, no, I already got it.
Sorry, say that again.
Yellowstone Park.
Yep.
Is also part of that whole thing.
Yeah.
As a shield volcano.
Yeah.
So, is that why the Old Faithful?
Oh yeah, all those geysers and everything. There's hot underground rock and magma that's heating up underground water pockets as well. In fact, Yellowstone National Park is a ticking time bomb. Probably sometime in the next 50 or 60,000 years, it may be the biggest eruption in history, to the point where possible human extinction, certainly changing the world climate for several thousand years. Similar to one of the ones that we think a meteor wiped out the dinosaurs, but there have been other mass extinctions, and we think many of those were due to huge volcanic eruptions that sent so much ash into the air that it darkened the sky for several hundred years, which Ice Age. Hey, Yellowstone National Park, enjoy it while you got it. I'm hoping to visit there someday at least, yeah. The San Francisco earthquake that you'll remember that happened in '89, since then, Old Faithful has not been as Old Faithful anymore. There's much more variation between how often it erupts. So that lets you know just how huge and long that fault is if an earthquake in San Francisco can affect Yellowstone National. Okay, that's big. The third kind, the last kind, and then we're done. Rift volcanoes. These are huge. These occur where magma erupts through long rift cracks in the lithosphere, the top part of the Earth's crust and mantle, primarily along spreading ridges. I mean, this is the classic in the movies, in a horror movie or fantasy movie, when the Earth splits apart to swallow the bad guy. That's technically a rift volcano, and the bad guy falls into the lava and screaming, except make it way longer. Okay? Most of them occur underwater. You may have heard about those hydrothermic vents that are underwater. Those are some associated with that as well. Usually not violent, but they release huge amounts of lava. Think of it as though you've got a huge tank of lava, but you've just opened the tap up to a tiny trickle, and it's going to happily trickle away for quite a while. Okay. what's your homework? Now, you're also going to have all Monday in class to work on this. So you don't have homework for the weekend. We are basically done the unit. So for today's lesson, you can try page 537, numbers 1 to 8 and 10 to 15 from your textbook. And then also chapter review, page 538, numbers 3 to 13, 20 to 22. And I did attach the answers to both of them here because I don't like giving you homework if you can't tell if you're doing it right or wrong. And some of the questions I thought were vague enough where I was like, what are they getting at? And then when I glanced at the answer, oh, okay, I see what they're getting at. Okay? So that's the textbook homework. Any questions there so far? I'll get you in a second. Okay?